This is the video for section 5.3 notes, slides 13 through 15. All right, so in section 5.3, we're studying something called related rates. But in order to do that, we need to go back into section 3.5, I believe, and that's where we learned how to differentiate implicitly. All right, so now it says if x squared plus 2xy plus y squared equals 1, differentiate with respect to time. Now, in section 3.5, we actually were trying to find like dy dx. But now I'm asking you to find the derivative, but with respect to time. So that means I'm going to take the derivative of each side with respect to t. So d dt of x squared plus 2xy plus y squared equals d dt of 1. All right, so now we're going to take the derivative of everything with respect to time. All right. So if I have the derivative, if I have x squared, what's the derivative of x squared with respect to time? It would be 2x dx dt, right? Remember, we're taking the derivative with respect to time. Plus, now I have 2xy, that's a product. So we're going to take 2x times the derivative of y, so dy dt, plus y times the derivative of 2x with respect to t. So that would be 2 dx dt, and then plus what's the derivative of y squared with respect to t? So 2y dy dt equals, all right, what's the derivative with respect to t of 1? That is, of course, 0. All right, so first thing we want to do is we want to make sure that we understand how to use the implicit differentiation process on, well, any equation that we're given. All right, and with any variables. Now, the key here is that there's actually not a t in the equation at all, right? So all of our derivatives should be followed by the chain rule, dx dt, dy dt, whatever, okay? And so the important thing to think about here is x and y must be changing over time, right? And so we want to be able to find that, all right? So now what we're going to be doing is we're going to say, okay, well, if x is 1 and y is -1 and dx dt is 2, find dy dt. So we're going to have a problem that says something like that, right? So then what are we going to do? Well, we're going to plug in all the constants here. So 2 times 1 times dx dt is 2, plus 2 times 1 times dy dt, which is what we don't know, plus y, which is -1, times 2 times dx dt, which is 2, plus 2 times y, which is -1, times dy dt, which we do not know, equals 0, right? Then, of course, we would continue and we would solve for dy dt. So we would get everything on the other side, and then we would factor out, and then we would have solved for dy dt. So back like we did in section 3.5. Now, this one, I guess I should have made it different. Instead of -1, how about +1? So this is +1 and +1. It just would have turned out to be undefined. So anyway, let's do that. 4 plus 2 dy dt plus 4 plus 2 dy dt equals 0. And so I would add the 4's together, which is 8, and then I would bring that over. So I would have -8 equals 2 dy dt plus 2 dy dt, so 4 dy dt. And so, as it turns out, then we can say, if I divide by 4, that dy dt must be -8 divided by 4, so -2. All right? And so that's the type of thing we're going to be doing. However, it's in the context of a word problem. And so there's going to be a few lines of text, and we're going to have to actually set up the equation oftentimes, and then we're going to have to kind of figure out what all of these different things mean. All right, so the directions. How do we actually do this? All right, so number one, okay, when we're going to solve a related rates problem, we want to draw a picture. Okay, oftentimes the pictures are very helpful for understanding what's going on in the situation. Sometimes they're not, but I would say in general that's the way we want to start. Number two, represent all rates of change as derivatives. So every variable in our picture, we need to make sure we understand whether or not that thing is changing or not. And if it is changing, we need to give a derivative to that thing. All right, and I'll show you what I mean. All right. Number 3, we're going to write this statement. Find blank when blank. So find, the value of this thing when such and such is true, right? All right. So that's number 3. Number 4, write a formula for relating the variables. So this is usually just kind of a geometric relationship or something like that. And then number 5, differentiate implicitly, usually with respect to time, almost always with respect to time. So remember, differentiate, that's what we just did. Find the derivative implicitly with respect to time. All right, and then 6, plug in the known values and solve. All right, so those are the steps we want to take to solve a related rates problem. All right, so let's take a look at a related rates problem. All right, so slide 15. A ladder 26 feet long leans against a vertical wall. The foot of the ladder slips and it starts to slide down the wall. At the particular instant when the foot of the ladder is 10 feet from the base of the wall, find how fast the top of the ladder is moving down the wall. Assume the foot of the ladder is being drawn away from the wall at a constant rate of 4 feet per second. All right, so a picture is definitely going to help here. All right, so I have a floor and a wall, and then I have a ladder leaning against the wall. All right, so the ladder is 26 feet long, so I'm going to put 26, right? That is not changing, so I don't necessarily want to give it a variable because that's going to make things more confusing. All right, so the ladder is 26 feet long. All right, now, when the ladder is stationary, right, it is a certain height, right? So I'm going to use h, a certain height on the wall, right? So that means the distance from the floor to where the ladder is touching is h. All right, then there is a certain distance along the ground. So I'm going to call that the base, so for b. All right, so that is the distance from the wall on the floor to where the ladder is touching. All right, so now it says the foot of the ladder slips and it starts to slide down the wall. So the foot of the ladder slips, right? So that means the ladder starts sliding. The bottom of the ladder slides away and the top of the ladder slides down the wall. Okay? So it says at the particular instant when the foot of the ladder is 10 feet from the base. So when B is 10, right, we're saying how fast is the top of the ladder moving down the wall. All right, so we have our picture. All right, so now what two things are changing? Well, B is changing, right, because the distance that the foot of the ladder is from the wall is growing, right? So we can say that there is a dB dt, right, which is some positive value. How do we know it's positive? Because the size of B is increasing, right? Okay. And specifically, it says, assume the foot of the ladder is being drawn away from the wall at a constant rate of 4 feet per second. So that means the dB/dt is 4. Okay. H. So the top of the ladder is sliding down the wall. So that means the height at which the top of the ladder is from the bottom is changing. So there is a dH/dt, right? And now dH/dt. Well, this thing is decreasing, right? H is decreasing. So it is some negative value. All right, but it does say find how fast the top of the ladder is moving down the wall. So that's actually what we want to know. All right, so now we've done step 2. All right, so look back. Step 2, represent all rates of change as derivatives. All right, so then 3, find blank when blank. All right, so what do we want to find? Well, we just said we're trying to find dH/dt. So our find statement is find dH/dt when what is true? Well, it says at the particular instant when the foot of the ladder is 10 feet from the base of the wall. So find dH/dt when B is 10, right? That's the instant that we want to know dH/dt. So that's our step 3, find blank when blank. All right, so step 4, write a formula relating the variables. All right, so one assumption that we're making, of course, is that the floor and the wall make a right angle. And so if we are relating h, b, and 26, that known quantity, they are related by the Pythagorean theorem, right? So I can say that b squared plus h squared is equal to 26 squared, all right? Now, okay, that is how the variables are related, right? So that's step 4. All right, 5, differentiate implicitly with respect to time. Okay, now it's very important that you do step 5 before step 6. So notice, b and h are variables. So when we take the derivative of b squared, we get 2b, and then remember, chain rule db dt. Plus, what's the derivative of h squared? 2h dh dt. equals, what's the derivative of 26 squared? Don't make this mistake. A lot of people say, oh, 2 times 26 to the first. No, 26 squared is a constant. Its derivative is 0. All right, so now, okay, we have differentiated implicitly, all right, with respect to time. So now it says plug in known values and solve. Well, what values do we know? Well, we know that we want to find DHDT when B is 10, right? So I can say, okay, well, 2 times 10 times dB dt. We know that value. It's positive 4. Plus 2 times h. Well, what is h? Well, think about this. B and h are related by the Pythagorean theorem. So if b is 10, I have 10 squared plus h squared equals 26 squared. We can actually solve for h, right? So how do we solve for h? Well, we could do it, conventionally. We could subtract 10 squared and square root, but you might also recognize that this is a 5, 12, 13. So h would actually be 24, right? This is a multiple of 2, right, of 5. So 10, 24, 26. All right, so h is 24, so I'm going to put 24 there, and then dh dt, and then equals 0. So now we have everything except for dh dt. So now I want to solve for dh dt. So how do I do that? So dh dt is equal to, I would subtract the 2 times 10 times 4, 2 times 10 times 4. Now, obviously, you could multiply those, and then we're going to divide by 2 times 24. So I chose not to just because it's going to make it easier for me to simplify a little bit. 4 and 24 reduced to be a 6. So I end up with negative 10 over 6, or negative 5 thirds. Negative 5 thirds what? Well, that's dh dt. So that's representing a rate. So it is the distance that h is measured in. Well, that's feet per unit of time. So seconds. So feet per second. So negative 5 thirds feet per second.